this Volterra type. So I will be both technical and not. I will not present proofs, but I will try to convey you some issues and that are behind a classical problem. And in stochastic control, we face problems written in this form. I hope you can see this little pointer that I have. I tried to find a different one, but I couldn't. So, so the question is rather simple to place, because we have a performance, which is this represented by this expectation. And this performance is usually appearing in this format, where the process we are looking at is X. I will come back to X in a while. U denotes the control, and lambda will be the time change. That also will come later. T is time, as you can imagine. And we have this performance organized into two parts. One with a functional G that give an evaluation of the final time of a process. And this time T is in the future with respect to us. Typically, the present is indexed by 0. And little f, no, big F, is actually another rate. So it's two different ways to write a kind of participation of X into an evaluation. This f can be of exponential nature, of power nature, and the same goes with a g. Typically, there is a kind of convexity involved. Then what we want to find is the maximum, or the process that gives the maximum, which is with the a little hat here. And the set of admissible controls is called A, and here it's indexed by F, because in stochastic analysis we have information that is running together with the process in question. So what we want to find is U hat that provides the maximum. And this is a fairly easy to set question, but it's also a very ambitious program, because one wants to find a whole stochastic process that from time 0 to time t capital will tell you exactly what to do in order to find this maximum. Actually, soup. Of course, you can reverse everything and find the minimum. The problem would be the same. And what is the novelty in this question that is really very old? And it's pertains to all different fields of applications. I have been more interested in economics applications or biological applications, but really it pertains to engineering as well. And the novelty that we present here is this, represented by the underlying process. And the novelty is on the one side, because this process, which is presented as a differential equation in terms of stochastics, so it's always integral, in fact, it's written as an integral, but we also call it differential equation, but that's the field. And the issue is that there is the presence of time also here and here, which makes this particular process memory dependent. So it means that this next, if you see a dynamic, which is a law that tells you how to go from step 1 to step 2, it says that this movement depends also on the past of the process. And Volterra equations in deterministic world are super studied. And there are many, many applications in biology and epidemiology. Here we have this term, and this term is the novelty, where mu here represents a random measure. And this random measure is particularly novel because it is not the classical Brownian motion, and it's not the jump process that is usually introduced, but it has a special shape, and this is written here, represented in these terms. So we have a random measure means that we are measuring a set, and that this set now is represented by this delta. This delta pertains to the time space, where the space R here represents jumps or no jumps, the size of this jump. So you see, if I have 0, it means that this component is continuous because there are no jumps. And if I have R0, it means that there are components of jumps of varying size in the real line. So this is the size of the jump. And of course, there has been a study about how to write down jumps properly, because we all know that big jumps are maybe from a probabilistic point of view well studied, and they happen. Of course, they happen, but so one can see different problems with different occurrence. But the problem in economics, for example, is the occurrence of small jumps, and that they are very dense. And the problem stays typically because it's a little bit the same problem that you have with convergent sequences or series, that small jumps can accumulate, and this accumulation can be either finite or explosive. So there are rules in here, and this goes typically under Levy studies, the studies of Levy noises, on how to describe properly small jumps. But in this particular case, we add an element which is time change. And it's not evident at this level, except that I have mentioned it in this little lambda here. It will come next. There is a study on stochastic Volterra equation and control. And these people that have been mostly involved have been Young. I have 2 papers in the reference for Young, and Oxendal with collaborators, particularly Agram. Techniques are completely different and background is different. For Young, it's only Brownian motion. So this mu would be a Brownian motion. For Oxendal, it would be a jump diffusion, which means that we would have both a Brownian motion and a Poisson type random measure. So these are 2 things that have been hanging around. The issue that is in common, and will be in common with us, in fact, is that these systems, because they are Volterra equations, they are what they're called non-Markovian, which means that they have memory, as I have said. And from a stochastic control point of view, this implies that one cannot use easily, or sometimes at all, dynamic programming principle, which is maybe the most effective solution method. Maybe in many cases it is. And so one has to resolve in finding sufficient conditions or necessary conditions via the maximum principle. And this is what we do. So what is it that we are doing? We have a time change. So this time change is a distortion of the timeline. The meaning of this is that we put like an elastic band on the timeline, so it can be stretched or it can be a little bit accumulated. And it's a technique to involve more noise into the system, which usually explains a clustering effect. So this has been studied in relationship with the so-called stochastic volatility, and an early paper around this is by Carr and Wu, but this is just the beginning of the story. The second level of novelty is the use of the technical use of non-anticipating stochastic derivative, which I'm quite happy to introduce it to you if you are interested in stochastic calculus, because it is a rather easy definition, and it is, though it is very recent, well, fairly recent result, and it is linked to stochastic calculus in the most classical sense, which is typically E2 calculus. Okay, the issue about using non-anticipating derivative versus other type of stochastic derivatives is the fact that with this kind of noise, there is no real alternative, because the other derivative which has been used is Mean-variance derivative, but that works for Brownian motion, works for Poisson random measure. There is an attempt by Jablonski, and I've also worked with it with Schursel, on conditional independent increments. But the real problem of using Mean-variance calculus in general is that the domain of the operators are substantially not really under control. And if you have to verify that something belongs to a certain domain, but this something depends on an unknown control, and the thing is fairly impossible. So some authors, like Oeksendal, for example, and co-authors, have used an extension of this calculus. This is an extension that you can find in my book with him on Mean-variance calculus. And this extension aims at enlarging the domain of these operators. Via that extension, effectively, one can do something, and that's fine. The extension is, on the other side, relegated to special construction of the space. And for our noise that I present today, this noise mu, that extension does not exist yet. We are working on it, but we don't have it yet. So for the time being, you will have to bear the non-anticipating derivative with me. So let's come to the practice of the noise description and the general framework. So first of all, we have this X, as I said, time is time, R represent the size of the jump. And as I said, you can imagine it divided in two. 0 stands for continuous part, no jumps, or jumps of size 0. And R minus 0, which is written R0 here, means the size of whatever jump is involved. This lambda, which is divided into two parts, so it's a two-dimensional process, describes the rate of time change. So you can have a time change for jumps and a time change for continuous part. And the time change rate is necessarily a non-negative process. If it was negative, it means that we would go back in time, which is good for the movies, but very hard to apply in practice. And there is a technical stochastic continuity involved and an integrability conditions. These two are rather technical. The first one is really a matter of good sense. And this big lambda is actually the time change process that appears as an integral of the time change rate. So it is effectively a family of time changes we are using, because in principle, one could use any non-negative process as a time change. And by F, with the subscript lambda, we have the information carried by this time change. Every stochastic process carries information as time goes about. And this is how the information of lambda is represented. A filtration means that these have a structure, these are family of sets, they are measurable and they are growing. So the family is getting more and more detailed as time goes by. F lambda corresponds to the last in terms of T capital. T capital is our horizon in the analysis, is the last, the biggest information available, and it will say everything about lambda. The issue typically is that information is revealed as time goes by. We don't really have the ability to look into the future. So this is what makes the difference between terminology like anticipating, it means that we look into the future, and non-anticipating means that we stick to the past and the present. which is actually what most likely we can measure at best. So the noise mu is divided into two parts. One part that is conditional Gaussian. Conditional Gaussian is where you have a double stochasticity given by the time change. I will be more clear in the next slide. That says that the distribution given the information provided by lambda is like a Gaussian. And this is the Gaussian density. Actually, the Gaussian, not density, but this, distribution function, phi capital. As you see, this is stochastic because depends on this lambda b, which is stochastic. And for what concerns h, we have a similar thing, but it is the Poisson distribution that kicks in, and it is doubly stochastic because this is the Poisson shape, but the term here is a stochastic. This is effectively representing a conditional distribution, the conditional law. What we also say is that mimicking the independence, now we talk about conditional independence given f lambda, given the information of lambda, whenever we have the two sets are disjoint. And the same for the Poisson case. They are conditionally independent. Moreover, both B and H are independent with each other. When we talk about independence, this is stochastic independence. That means that the laws, the conditional law in this case, no, when the joint laws is represented as the product of the laws. So in general, now that they are conditionally independent, it would be that the conditional joint law is represented as the product of the conditional laws. Typically, a time change has been seen in this way. That means that instead of write a process, I take out the time of the process and I replace the time change process. So this result due by Serfoso in 72, so that's not an early result. It is exactly explaining this. It's saying that if you have this kind of conditional measures, and I'm pointing to the Gaussian case, but then it goes also for the Poisson case. If you point to the Gaussian case, the conditional Gaussian measure is the same thing in law, in distribution, to a time-changed Brownian motion. So W is a Brownian motion independent of lambda b. And instead of looking at W time, you take out the time, replace the whole process. This is the most used representation of time change and explains this idea of putting an elastic band on the timeline. And what this result says is that if you have the properties that I have mentioned here, A1 and A2, then B, this measure B, this conditional measure, is a time-changed Brownian motion. And the other way around holds too. So these two things are equivalent in law. And the same is written here for what concerns the jumps aspects. Okay, so this is why I keep talking about time change, even though from a calculus perspective, this representation is more suitable. And okay, next point, the information. We have different information flows. Every stochastic process we introduce has one, but we focus the attention already on the F lambda we mentioned earlier, and then we have other two, F and G. F is the smallest filtration to which mu is adapted. This means that mu it is effectively the filtration generated by mu, and then there is a kind of right continuous version of it represented by these intersections. The second, it's a non-realistic filtration. is so-called enlarged filtration, in which we imagine to take these ones and to enlarge it by the whole knowledge of the time change process. The reason why this is unrealistic to use is because this part of the information is in the future. So from a usage point of view, it's not realistic. From a mathematical point of view, it makes a lot of sense, because if we know f lambda, then we work better with the information and the knowledge of the noise. So we have a mathematical level and we have an applied level. And our work will be to go from one to the other every time it suits. Important points is that GT, the last of the G, is the same as the last of the F, because at the time T capital, this is known effectively, because if you arrive to the future, to the horizon, your horizon will be the present and then will be known. On the opposite, if you look at the first element of this filtration, in the case of F, it will be substantially trivial. In the case of G, it contains the whole information of the future time change process. And this is the reason why I say it is an unrealistic filtration to use, but it is mathematically convenient. Important points. The noise that we have presented is a martingale in terms of a random field, where a random field is used because I call processes things that move only in time, and fields those that move in the time space, in which case, in our case, space means the jump size. This is a martingale. Martingale is the element to which Ito calculus works fine. And this is a comment about the anticipation we have already given. Now, other elements are about the non-anticipating derivative. This is an element of the Ito calculus. You have some references of an early job. Another one, which is more related to random fields. This is the inner construction of the calculus that gives this result. And when I talk about calculus, I mean Ito calculus here. The classical stochastic calculus is Ito calculus. So what we say here is that if you are given one random variable and you are given the noise, which is mu, what we are making the integral against, then the non-anticipating derivative, which will be called NA derivative later on, is the limit in the space of L2 P times lambda. This is the product measure, and lambda is stochastic, so this you have to take it in the good order, first lambda and then P. And is this limit of these simple functions phi n. The whole Ito calculus is constructed on simple functions, also called simple integrands. And they typically have the shape of simple functions, where this is a characteristic element of delta, is the indicator function. It's called in probability, sometimes it's called characteristic function in analysis. Though characteristic function in probability means something else. So the terminology, depending on the field, is dubious, but this means that it's one when the point belongs to the set that is written and zero otherwise. So this is a step function. The elements of the step are stochastic and they are represented by this conditional expectation. The conditional expectation is given the information G in this application that we are presenting, and it is related to the time S and K, and it's exactly this time, and it is very important that it is the left end of the interval of interest when you look at time. this product, zeta is here, the random variable, and here you see the noise and a normalizing factor down here. So this product is in L1 because both elements for their nature are in L2, so this is well defined as a product. Coming back to the choice of S, it's all related to here. So this is a generic element of a partition of the time space. And this partition is done, being a product space, is done on products. And it's not well described now in these slides, but it is what is sometimes called nested dissecting system. So you chop up the space in ways. The M gives the level of refinement, the K is the counting of the sets, and the higher the level of the refinement, the narrower all these sets become. So you have a whole family of these simple functions indexed by the refinement, and as you see, the sum is over the elements of the dissecting system with refinement N. I go back to put emphasis on the choice of the left element. This is important for the Ito calculus because it takes into account the fact that this process is adapted to the filtration. Even better, it's predictable with respect to that filtration, which means that it is an appropriate integrand for Ito calculus. And so the limit is an appropriate integrand. All integrands that are G adapted are written, denoted, the set is denoted by integrand G here. Okay, so the result that is linked to this derivative is the following. It says that every random variable can be written in stochastic integral terms. And this is written as the sum of an element called the remainder and an integral part. And this derivative represents exactly the integrand into this integral part. This may resemble the fundamental theorem of calculus if you want, but in stochastics, differentiation has come very late in the history compared to integration, and is still matter of research nowadays. Completely different from classical analysis where you had Newton coming first and Lebesgue coming much later. Of course, we had some others in between like Riemann and Stieltjes, etc. But in some way, differentiation came earlier than integration. But that's the opposite in stochastic analysis. And we know that this one is expressed directly in terms of what you have to differentiate and towards what, that is the measure mu, which is stochastic. Okay, this remainder is orthogonal to the integral and is characterized by derivative 0. In the case, now I come to this talk, in the case of filtration G, it has a particular shape, and this is the shape of reference. So we have an integral representation of this type, explicit. Explicit means that we can write the integrand. The fact that the representation exists, this is well known from earlier. Okay, coming down to the control. The control is studied, as I said, with maximum principles. And they substantially move the solution to the definition of an Hamiltonian functional, mimicking the maximum principle in deterministic terms. And in this particular setting, here I wrote down properly the assumptions on the F and G in the performance functional. And U is the values taken by the control map. And at this level, I don't think it's you will read this quietly. I continue with the Volterra dynamics, and in this slide, I wrote explicitly the precise definitions of the coefficients B and kappa that are present here, which requires some regularity, in particular some C1 regularity with respect to T and X, and integrability of those derivatives. Now, this, of course, it's a general statement. If you have particular cases, then you can, of course, work with more, with stronger results. Typically, these have memory, as we said earlier. Now, again, in here, just to say what is known, I point to the fact that the existence of the solution of this type of equation is a matter of concern in general. And here it's written sufficient, the set of sufficient conditions guaranteeing existence in terms of F adapted solutions in L2 and their unicity. These are, of course, only sufficient conditions. They are in line with classical results. One can recognize, of course, here there is some form of Lipschitzianity. Here there is some form of linear growth. But what you see in the specific is the appearance of this lambda in the different points, and this lambda is the time change process. So it's a little massaged in order to accommodate the presence of this time change. The Hamiltonian functional, it's typically associated to a first variation process, but in the stochastic terms, it's not directly, and it is associated to the solutions of a backward differential equation. So a backward differential equation is a differential equation that knows the final point and scrolls back in order to find the initial point. In reality, we call solution of a backward equation both the process that allows you to go from time zero to the target at T capital, but also it's a pair. It's the process that I said y, and the pair is given by phi, which is the integrand in the stochastic term. So the solution of a backward differential equation typically would be a pair, not just one process. In our particular case, we are dealing with Volterra type equations. And then things get more complicated because there is this memory effect to take into account. And in this paper, we have the proposal of having an Hamiltonian represented by the sum of two functionals. The functionals are all from the time. Here you have the time change component, the control component, the process component, the solution of the backward will be here. And in here, it will be the other bit of the solution of the backward. So this y and phi are in here, two spaces that have a description in this line. And this one is, oh, I didn't write it, but this is the solution of the backward. It is also stochastic in its own terms. And then, but it's a functional because the values are real. And it's split in two. The first part is classical in some way, looks the same as for a jump diffusion. And the second part is only due to the Volterra component. And all of them contain the time change. I would like to point the attention that the Volterra bit of the Hamiltonian depends on the derivative of the coefficients with respect to time but also to the non-anticipating derivative element here. Now, this is an educated guess, shall we say, to write down this type of Hamiltonian. The use of them is clear in the proof. But the point that I would like to stress is that the y and the phi that here appear will be replaced by the solution of this backward differential equation, where you see that here you have the component g of the performance. Here you will have the derivative of h that contains the f, which is also part of the performance. Okay, so the problem that is faced then is to find the solution of the backward Volterra equations. So we move now to study backward differential equations of Volterra type. And here they come. Typically, you can have many shapes, but this is the one we treat. You have that the time is t, is running from 0 to t capital, and it looks into the future in here from t to t capital, because the knowledge is really linked to a given process, xi of t. And g is called the driver, is the coefficient of the equation. And the driving noise, sorry for this driver and driving noise, but we have both, it's mu. The unknown are both y and phi. And to study backward differential equations, it's fundamental having an integral representation result. And we have this result because we have it given by the non-anticipating derivative. And this is what helps us to find the solution of these equations. The result with the assumptions providing the unique G-adapted solution is here. The driver needs to be adapted and satisfy with all the elements satisfying the right integrability conditions. They belong to the right space. The driver with the points as zeros is finite in expectation. Here you recognize a form of Lipschitzianity in y and phi for fixed t, s, and lambda, where this equation is written in terms of the time change component as well for the continuous part and the jump part. And once this is in place, the nature of the assumptions, I would say it's very classical in backward differential equation. It's only really adapted to the context of Volterra and of time change. But the solution is guaranteed and it's unique. And this solution is integrable substantially in L2. This is what it says here. It should be written less than infinity though. Okay. Among the many backward differential equation of Volterra type, in order to solve our problem of control, we need the linear case. And this linear case, you see it's linear because the y in the driver appears in linear form. Phi is always appearing in this form. And this gamma is the other bit of this product. And it's taken to be bounded as a sufficient condition, but you can do better. This particular shape admits an explicit solution, and the solution is written in terms of process defined by recursive integration of this gamma parameter here. The whole series is bounded. We can prove that this is converging. In particular, it's easy if gamma is bounded. And psi capital is the series associated. So the solution of that linear equation is in two parts, as expected. And the first is the y, and it's given as the conditional expectation of the known process. And this psi I've described before, and this is the coefficient substantially providing this. So this y is explicitly given in terms of the input of the problem. The component of phi is given in terms of the non-anticipating derivative. And oops, sorry, I've lost it. Here it is, back. It's here. The derivative of this process u, and u in itself is explicit. Psi is a part of the problem, gamma is the parameter, y appearing here is corresponding to this formula. So quite remarkably, we can have an explicit solution of at least one backward stochastic differential equation of Volterra type. And we use it for the stochastic control terms. This slide is presenting the assumptions on the control problem, the coefficients of the control problems. This is the Hamiltonian. These are the coefficients of the forward equation, the controlled equation that we have, B and kappa, that are summarized and tailored. So these are the summary of the conditions that I have presented earlier, but written for the equations appearing in the control. Under these assumptions, all the theorems we have mentioned to be useful can be applied. So the maximum principle. The first thing is to recognize that we can give sufficient conditions to find a maximum. And sufficient conditions means that if you have an educated guess of what would be a control, then you can verify that this is effectively the optimal control. But it's only sufficient conditions. We start with that. Of course, if you cannot apply a sufficient condition, typically you are left naked because you don't know whether it is optimal or not. So next is to provide a necessary maximum principle that provides how to educate your guess, so to speak. So this is the process we are taking, and we start with a sufficient case. But even earlier than that, we need to tailor the Hamiltonian and all the calculus that we have presented under the filtration G, the mathematically good filtration for us. We need to tailor it to the realistic context, and the realistic context is the information provided by F. So we need to write a new type of Hamiltonian. I still call it Hamiltonian, even though it's not linked to a backward differential equation itself, but it's just for simplicity of notation. But it is effectively the projection of the earlier Hamiltonian that we wrote before, divided into two parts, where the solution of the backward differential equation for, in the case of control U, is inserted. So this is stochastic, it's a G measurable, and then we project it with conditional expectation onto the information F. So this operation, being H script split in two parts, provides a natural split in two parts. And what you see here, down here in these lines, long written but not difficult, are exactly the contribution of the two parts projected, or conditional expectation, that's the same. So this is the explicit format of the so-called Hamiltonian under information F. So the sufficient maximum principle runs as follows. It says, if you have a process that you think it is optimal, it belongs to these F-adapted portfolios, it's acceptable. And then I call X hat y hat, phi hat, the corresponding solutions of the forward equation. This is f of u hat, basically, and the corresponding of the backward equation. Okay, then I can write the hf in here. And what happens? That I substitute this hat to the function and let this u run free. But if this function, the function of x, in x, of the sup of this Hamiltonian hf, which is stochastic, this is a stochastic element, it's a concave function. This is the only thing I have to verify, that it's concave besides existing, of course, because if it is explosive, then we are out of the case. If it is concave, then I can tick this property, this point done. And the second thing is that if I take the expectation of this element here and I work out the sup of the expectation, note, I don't take the expectation of the whole lot. I first take the expectation and then the sup. And I verify that this is realized by this educated guess, exactly this one I picked. Then I can conclude that this guess is optimal. So this is a very strong result if one can apply it, which means that there is some concavity here request. That can be a little difficult sometimes, but if one can apply this, it basically blows down to make the verification that a functional is either concave or to find the sup over something which is in the set of values of u. And of course, this set can be one-dimensional, which would make things easy, and more complicated if you go up in dimensions. But at least it would be a subset of typically real numbers. This is the catch of these results, because it blows down to find conditions on a space that is not anymore stochastic in this sense. So this is the philosophy behind the sufficient maximum principle. As I said, this concavity, if you don't have it, then you don't know how to apply this result. And also, how do you find an educated guess? So it comes the necessary maximum principle. And the necessary maximum principle does not require any assumptions of concavity or anything of the Hamiltonian, but it requires that one can make a permutation, a little shake of the system in order to express, to find an equation that, if solved, provides the sets inside which you can find your optimal. So let's go together. We see that the assumption is that the set of admissible controls is closed under permutation, which means that if you have any element belonging to this set and you change it a little bit, where by little bit we mean by an epsilon component small enough, beta is just a simple permutations, and this is step functions type. This is still admissible. So we want a kind of a little ball around this U, so that we can substantially make derivatives. And in fact, the issue comes here, because we know that a necessary condition for optimality is provided by this situation, which means that if U hat is your target and you shake it up with this permutation, the derivative with respect to epsilon evaluated at 0 is null. So that's a flat point, right? Substantially. So we know that this is necessary for any maximum. The point is that we can reverse this equation into this equation. And this equation is written in terms of the Hamiltonian. And it says that if U belongs to this set and satisfies this condition, then we have that also this equation will be satisfied. And this equation is written explicitly in terms of the Hamiltonian function which we have. And not only, we can also reverse this result so that these two are completely equivalent. Okay, so now the idea would be that first one tries to solve this equation, gets an educated guess, and if possible, applies the sufficient maximum principle. If not, one is left to do hard job, ad hoc, tailored for the particular case. We have applied these results, and this is really the last two slides, but I'm not really showing much because it's, of course, it's a lot of computations and they look very nice, nasty because they are long to write with all these integrals, but not necessarily complicated. We have applied it to find an explicit solution to this problem, where the performance is written as a polynomial, and this one is the mean variance portfolio selection problem. So the problem goes running in this way, that you have a market and U is your portfolio, and the portfolio is providing you with a wealth process. Here it's only the wealth process written, not the market. But let me say that rho is the interest rate in the market, and the little gamma and big gamma are the elements of the coefficients of the price of the commodity in question. And these prices are memory dependent in the sense that they are in commodities, the price often depends on the path, the history of the same commodity in the market. Anyway, we come to a kind of wealth that is written exactly in this way, of course, because for us it mathematically is an example, though it's a motivating example for this study. And we have applied the necessary maximum principle and then the sufficient maximum principle. And in this particular case, we end up that we need to solve this particular equation in order to find the optimal. And this equation that is written in this sense can be written explicitly with all the bits and the pieces that are important there. And then we are in the process of doing simulations to find a numerical solution of this equation. But things are quite promising, and theoretically speaking, we are left with solving this one equation to find the solution. Still not easy, but much better than it looked before. By this, I end, showing you some references, the ones that I have mentioned. We have the works by Oxendal and Young. We have the non-anticipating derivative here. We have some Malevin calculus in this paper and the Jablonski paper. We have some elements, early elements on linear Volterra equations in this work by Hu, and just an application of time change for those that are interested, though it's very, very partial, and anyway, it's one of them by Carr and Wu in the context of volatility in this paper here. Thank you very much for your attention.